Welcome to day 2 of 12 of the 12 Days of Commodore's Christmas album, 1982. That's the full name anyway. We're here today to follow up on what we started talking about yesterday. If you didn't watch yesterday's video, you should jump back and have a look at it. It's maybe 10 or 15 minutes, and it starts with Commodore's Christmas demo and talks about what we're here to achieve. Today, day 2, we're going to cover, I guess, 5 or 6 things here. I'll quickly walk through them. To start with, we're going to introduce analog synthesis, talking about the fundamentals of sound. The caveat or the disclaimer is there are thousands of videos out there that talk about this. I'll try and be brief and to the point. I'm talking about this in the context of the SID, because the 6581 SID chip is what we're all about here. And so I'm going to roll a video of me messing with my Minimoog, and I say messing. I'm not a musician. I can play bass pretty well, but when it comes to keyboards, I'm more of a collector and a hobbyist, and I like to repair them. But I'm going to roll a video in a little bit that kind of walks through the differences between the Moog synthesizer and the SID chip. Then we're going to dive into the spec sheet for the 6581, which was a very interesting artifact because it was produced or written probably in 1981 as they were making the chip for the first time, and I'm not aware that Commodore ever sold it. It was more of a very thing that Jack probably wanted to keep to himself and not let that out of the gate and let others use it. Before you know it, Atari could have come along and produced a system with 4 SID chips in it if he was licensing them. And yeah, it'd be great to make a couple bucks, but he'd probably rather sell 18 million units of a system than let something that was kind of a real competitive edge into the hands of others. But nonetheless, the spec sheet exists. We're going to walk through an updated spec sheet that I managed to find, and then we're going to move on from there and talk about how you would connect this chip to a CPU, a Ben Eater style. Of course, Ben Eater is a YouTuber and an educator, more so, that does a lot of things with analog and digital electronics. His digital series is really the best. I mean, he has a bunch of things to talk about, a CPU integration. He builds his own CPU, and he does a lot of things with 6502 that you can learn a lot from. I certainly have. So we'll talk about that at least in theory. And then we're going to look at the SID data we started last time, which is the Rudolph the Red-Nosed Reindeer song from the Commodore Christmas demo in context with what we've learned so far. And then finally we'll talk about what I call Guru Mode, which is an introduction to some add-ons to the Commodore Christmas demo. We'll run without the Christmas tree on the screen. We'll need the full screen to kind of look at the data occurring as the clock rolls and as data bytes get thrown into the SID chip. But I'll be working on this, and I'm probably going to show this 3 times across the series. So I'll do it tomorrow. We'll do it after the 6th episode, and we'll do it maybe one more time at the end, or 2 more times at the end. So I have to see how far. I have a really something big planned for the end, for the 12th day. Not sure if I'll make it. It depends on how much time I have to code. But let's jump right into it. So I'm going to roll the video now, and we'll be back in just a moment to kind of talk about the third item here. Anyway, this is a Minimoog. It's a 76 Minimoog. I bought this from probably the second owner, but it's in rough shape because they took it on the road. It was actually owned by a band. It was owned by a band named Blue Oyster Cult, which was a 70s and 80s rock band, relatively popular in my part of the world anyway. They burnt out like all the rest of the rock bands. But this was their Minimoog. I bought it from them. It's in pretty good shape, well maintained anyway. It doesn't look like it's any kind of shape. But I'd like to talk to you about the controls, the similarities, the differences between this iconic instrument and the 6581 SID chip. Bob Yanes, I think was his name, who was kind of designer behind the SID chip. That's his synth chip, SID chip. He must have had this in mind. This machine was manufactured in 1976, although Moog made these from the early 70s up through, I think, 82. Bob, I believe was his name, I hope, I'll correct it in the comments if I'm incorrect here. But he probably had this in mind as he designed the chip. And the reason is that it's got 3 oscillators, just like the SID chip. The SID chip has a noise source. SID chip has envelope generators, though they're actually better than the Minimoogs. The SID chip had the ability to do pitch bending, all kinds of things that were very current in terms of technology in the late 70s, early 80s. So I'll start by saying that there are 5 things here that I'm going to talk about briefly before we get back to the SID chip in the lab, so to speak. And they start with oscillators. And the oscillators here are very common to what was available technology-wise or from a technology perspective in the early 80s. And there are waveforms, which is the basis of the sound. I'll turn off all the business here just so you can hear a single waveform on, and I'm going to pick the, I guess the sawtooth wave is a good one. Hear that? That's the envelope doing its thing with the filter. I'll turn the resonance way down. So it gets more bassy. I'll turn the filter all the way open. So you can hear the raw waveform. That's a sawtooth wave. The SID chip has one. This is a triangle wave. You probably barely hear that. Very round, not woody, but round and bassy, this tone. And at the right volume, this could really shake the house. But it's a kind of a quiet, subdued tone. And I believe Silent Night uses this in addition to some filtering. The next one in common is the pulse wave. And there are 3 on the Minimoog. They're kind of a hard fix at a width of probably something that's more like a square wave. Another half of a square wave duty down from there. And then a very woody, nasally, very thin pulse. And it's hard to hear the difference between a square and a sawtooth. Once you start filtering it, adding resonance, you can kind of get the difference, at least in person. Maybe through the microphone doesn't quite pick it up. But the Minimoog has 3 kind of full range oscillators with a selection of 6 waveforms, but ideally it's really just a sawtooth, a triangle, which is the bottom, and a choice of 3 fixed pulses. The 6581, on the other hand, has a sweepable pulse width modulation. So you can change the width and modulate it across time if you like, which is a very common effect in the 80s. Synthesizers that came after the Minimoog. So that's the oscillator section. Again, it's 1 for 1. Now I'll talk about the mixer, where you can adjust the volume of each of the 3 oscillators independently. So that's novel. And then we'll talk about a noise source, which on the 6581, you've got a noise source as a different selection on the waveform. This does not. This is a single noise source, which gets mixed in up. You either have it or you don't have it. However, there's a choice of noise type. So I'm going to turn off this oscillator, turn on the noise. White noise, pink noise. I don't know if you hear the difference or not on camera there, but I'll use the filter to sweep it. And pink. Pink's much more rumbly, lower frequency. And of course, I'm not sure that the 12 dB filter that's built into the 6581 can do what the Minimoog's filter can do. This is a 24 dB filter, and there's something special about it. In fact, Bob Moog, this is not a Bob Moog history lesson, but Moog, I think one of the few patents they have is for the 904 low-pass filter. The filter here is similar to the Commodore 6581 filter in that it's one filter for the entire synth or for the entire chip. So all 3 oscillators are mixed together and kind of placed into a filter that could be having a high pass, low pass, or band pass at a certain frequency range with a certain amount of resonance before it gets sent to the output stage, as it's called. Here, we really only have a low pass filter. So again, the 6581 is somewhat superior in that regard, that there's only a low pass filter here. Of course, modular synthesizers, which is kind of where the Minimoog came from. I'll quickly turn the camera to part of mine. I've got a full complement of all different types of filters that are available at kind of at the day, and very similar to what the SID chip can do, but at a higher level, so to speak. And then finally, there's the modifiers, which are envelope generators. So I'll go back to the beginning. Oscillators. There's a mixer. There's a filter. There's a loudness control or a 4-stage envelope, and that goes to output. One other concept to add, and I'm running through this because I don't want to waste all my time on it, but that's the concept of gating. So this is noise still. Turn the noise off. Turn on an oscillator. When I press a key on this, the envelope generators will begin, and I'll put a 600 millisecond attack time, a 600 millisecond decay time, a sustained level of like 4, and I'll turn release decay on. It says decay there, but this is really the release stage on a Minimoog. Turn the resonance down. Okay, makes it a little bit longer, a little bit longer, a little bit higher. Okay, picture, if you will, the volume rising, right? It rises when I press the key, it's gate on. It reaches the maximum volume. It decays down to a steady state, which is the sustain level. And then when I let go of the key, it releases. That 4-stage envelope is exactly what the SID has. So I'll just draw it real quick in the air here. Okay, that's a super important concept, and that's what they use to actually ultimately shape the tone of any kind of synthesizer. And I should probably add that I mentioned in the intro that this is subtractive synthesis. It's analog subtractive synthesis, which means you start with a very basic tone that's full and raw, and you subtract elements and harmonics from it. And you change the loudness of it over time. You have the maximum tone that's the highest it can ever get, and you can remove things from it or fade things in and out to get ultimately the sound that you want. And that's really the job of the synthesizer, is to recreate or synthesize or simulate other tones. And I'm pretty much done talking about this. Let's move on to the lab, and we'll see how this applies to the SID. We'll talk about the next steps in this project. Okay, so a bit of a rush job, but you get the point, and you see kind of where synthesis was in the early 70s through the early 80s, at least from a Moog perspective and from when SID hit the market. So I'm now going to jump into the spec sheet, and we're going to talk about how those things correlate back to the SID by looking at some stuff on paper. Now I should mention that I'm going to post the kind of 3 artifacts, which are this data. I'll post a link to this. I'll put a PDF someplace. The spec sheet, of course, also, and maybe some of these slides, so to speak, or this one at least. So let me switch over here to the spec sheet. Here we are. I'm going to start at the top. As mentioned, this is an interesting document. It's one of the most poorly written documents and one of the most easily understandable documents that I've seen as far as spec sheets are concerned. Maybe it was a sign of the times. Not sure, but there's a lot of there's a lot in here that a layperson, me, can understand. If you know a little bit about electronics and a little bit about SID music and the capabilities, you can get a lot of information out of this. And my favorite part is this part here in blue, which is the table that shows all the registers and all of the values and what they mean. So this is really handy. But let's start at the top. Okay, so here we are. This is the February 25th, 1986 update. And you'll see some, again, this is a 10th generation copy of a copy of a copy, which is kind of funny. But and it also says it's stamped preliminary because it probably was never released, as I mentioned. So let's talk about the pin configuration. I don't want to get too much into hardware, but I think it's important and interesting, and interests a lot of people. So let's dive into it. This is a 28 pin DIP, right? A dual inline package. There's 2 rows of pins. It's the same pitch as what the CPU itself makes, right? Uses, I should say, the 6502. So this is a 6581 series, and it's got a series of lines which may look familiar if you've ever looked at a CPU, pinout, which are data lines labeled D through 0. In fact, on the Commodore, on the 6502, they're on the same side of the chip. I believe it's the same pin numbers relative to the fact that you've got 20 on each side. then you've got the address lines here on the left side. And the address lines are numbered 0 through 4, so there's 5 of them. We'll talk about why there's 5 of them in a minute. There's also things that the chip needs, like read-write select, chip select, right? There's other things, a clock, that it needs in order to function. Then there are things that are interesting, add-ons, or things that you can say, oh yeah, that makes sense. The potentiometer input on here. This had an analog to digital converter built into it, and it could correlate a voltage coming in with some resistance, I should say, resistance of a potentiometer, which is the X axis. Well, there's an X and a Y, because it can actually support a analog joystick if you had one. But from the sake of the paddles, it'll support 2 paddles plugged into this chip. So that's another function it provides. And there's a third function it provides. It provides a random number generator for Commodore Basic and for machine language, for that matter. So if you use the RND function, it gets it out of this chip. There's a white noise running all the time, and it does basically a sample of that white noise source and ends up with a number, which is interesting. And then there's a fourth thing it does. It will accept external input, which is this line, and it does some things to mix it with the tones being produced by the SID, and it lets you, I believe, filter them through the filter, which I've had some I won't say success with. I've had some failures with. Well, just one. The time I blew out my SID chip because the signal I sent into was too hot. So yeah, I mean, I'm probably not the only one, but maybe I'm the only one in a couple mile radius that have done this. But in any case, let's move on. Now we're on to my favorite part of this document, my favorite page. This is a memory map. And again, voice 1, voice 2, voice 3. Each of these 3 are identical. Each one has the actual byte values, and each one has columns of bits. So this is important. We'll get to that in just a moment. Oh, also it tells you which one of the registers are write only or read only. So you've got a mix here. Oh, guess what? The pot is only read only. Here's a typo. RIS. This is the stage of the envelope generator, which is the release stage. So remember, we talked about the envelope in the video. There's the attack, decay, DCY, sustain, STN, and release. So originally, I guess, it's kind of odd actually what they're using, ATK. I don't know if I'd call it that. Sustain is usually SUS. But anyway, that's one typo I guess they fixed. So let's talk just briefly about bit values and byte addresses. If you can picture this address here, the 0, as D40 in front of it, and then D4 here, D410, these are literally the addresses of where this chip plugs into the Commodore 64 and to any of the Foenix machines that uses a SID chip. And I may be misspeaking when I'm talking about the 65816, but at least for the 6502 machine, like the F series line, the F256, these are the addresses. So D407 address is the frequency low for voice number 2. And we'll see that directly as mapped out in data in just a moment. So today we're going to talk about 3 bytes. We're talking about the frequency, low and high. And we're talking about the control register, which lets you select waveforms in the upper nibble, as it's called, right? These 4 bits are nibble, and other things, which include, in our case, importantly, the gate. So the lower nibble of the control register, which is identical between voice 1, voice 2, voice 3. It's not shared, but it's the same on each one of these things. The gate is super important, and the gate is, if you recall, the point at which you press the key down on a musical keyboard, and it actuates the VCA, or the voltage controlled amplifier, or the volume, so you can start to hear the tone. Basically what it does is it kicks off the envelope generator, so then it can actuate a tone, and when you let go of the key, then the second stage of the envelope generator commences, which is this bottom part here. It's the sustain and release, but really it's the release part, because sustain is really just a level. So there's the 3 voices, and then we'll talk about this next time, which are the filter, and we'll talk about oscillator 3, random, and what that's all about. I'm not sure what it's about. We'll have to check into it. Certainly the random number generator will seed some parts of this with a random value. Now I hesitate because some synthesizers, some chips have an ability to crack off part of the block and use it for an alternate purpose, and certainly the Minimoog itself, I didn't talk about it in the video, but the Minimoog itself lets you switch voice 3 into a low frequency mode and use it to modulate something in voice 2 and voice 1. And that's usually the filter envelope, or it can be the pitch. So you can use that to modulate and make a warble or a vibrato in the tone. And this may have something to, I've never even played with it, to be honest. So I see it down here. I wonder what that's all about. There's a third envelope for something. And then there's a third oscillator or an OSC3 here for something. So I'll have to look into that, and maybe I'll report back later on in the series. I'm not going to spend a lot of time on it in the next day or two or three. Moving on now, register descriptions. You can read this. And as I mentioned, this spec sheet is pretty easily easy to read and understand. I think they did a nice job reading it. It's certainly not necessarily for engineers. I'm going to move down now through this second page of this. One other thing to point out on this page, though we're not talking specifically about envelopes today, we'll talk about the rate and how this thing works. So if you recall, when I was playing, talking about envelopes, I set the two knobs of my Minimoog to 600 milliseconds. I said, let's have a 600 millisecond attack. Here you don't have that choice necessarily, because this is a digitally controlled analog synthesizer, so to speak. So the waveforms are analog for sure, but the control of them are digital. And really the reason it's that way is because they don't have the enough address space to have every single, if they had one for each millisecond, think about how many bytes of memory you would need. So let's move on from here, and we're getting it down to the next stop, I guess. There's potentiometers, there's the random stuff I'll talk about, I'll read about, learn about, and then I'll bring it up later. More about the pin description, voltage, not that exciting. SID timing, very exciting if you're an integrator. Okay, here's one. Equal tempered musical scale values. This is essentially how you make this thing play a note that is going to, hopefully be in tune with an analog instrument of some type, or certainly in tune with each other, which brings me to something funny. My SX64 that I used to, I take it back. My X64 Vice emulator in this Macintosh that I used to record the SID demo plays at a certain frequency, and my my back SID chip in my F256 is completely out of tune with the emulator. It clashes. It's just amazing. But it's important for Commodore to have a chart that told you precisely that A440, otherwise known as fourth octave A on the musical scale, 440 hertz, can be selected by plugging these values into byte 0 and 1 of each voice. Now, of course, this is not an absolute list. This lists all the way up to what? B7, it goes 7 octaves, right? It starts at 0. So this is C, the note C on the 0th octave. It goes 8 octaves in total, up to 7, up to the high B, which is, that's a tremendous range. And to stay in tune as an analog synthesizer with a chip is a pretty big feat, I think. But the nice thing is that there are bits in between. So if you slid from, say, a 440, and over say in a second, you threw bytes at this thing, not in a second, maybe in a second. If you threw bytes at it evenly across a second in these 12 intervals from here to 880, which is the next highest A, it essentially, you're doing a pitch bend, and then back down again. So there's a lot, you've probably heard it in a lot of SID tracks, especially some of the well-produced stuff. They do all kinds of things with trills, with slides. This table is important, and you'll see in almost every piece of SID music, you'll see parts of this table represented in data bytes, and we'll be doing the same. Of course, in the data we'll get to in a second, you'll see the frequency values bound to byte 0 and 1 of each of the phrases, for voice 1 anyway. And what's the selection of notes used? Well, we can write some code that will pull that out and place on the screen. We're not going to place graphical quarter notes, dotted half notes, all the rest of it on a grand staff, as they call it. But we'll at least put the notes on the screen. So we'll be using this table to do that. Here's a good one. This is a change all dollar signs on this page to a number sign. This is a note. You can say this is Courier. This is Helvetica probably, or an Arial font. They didn't have a lot of fonts back then, but somebody literally put this into a typewriter and typed on here. They should change all the dollar signs to number signs. Why? Because for some reason, whoever originally created this, probably an engineer, felt that D4 dollar sign, otherwise known as D sharp, You should use a dollar sign to identify it as a sharp. Well, no, that's kind of a stupid idea. Maybe it's a, is there an S? Maybe it's an S. No, it's a dollar sign. It's a dollar sign. Anyway, that's one of the changes to the update. Pretty amusing. Here's a bunch on envelope generators. Here's a picture. Well, yeah, I could talk about it this way. Connecting a CPU or connecting a SID to a CPU is really no more complicated. They're running straight wires from the address lines on the CPU to the SID chip. And Ben Eater interfaces, I think what is the interface? Like a 60, some kind of a controller, not a 6526. One of the MOS controllers, he interfaces it directly to control an LCD screen. And he talks about the address space and how he would mask it. And well, that means he can't use some parts of memory. Because if he has RAM tied into the same bus, right, which is what you would do, you're losing access to 1, 2, 3, 4, 5. Of course, you've got 16 address lines on a 8-bit CPU that'll give you up to 65536 in terms of memory, the 64K footprint. But giving away this much of it really is a major disadvantage. Of course, if it's a single-purpose device, like if I were to take 2 SID chips and place them inside of a MIDI connected box, it might be good use of the real estate, at least on the bus. But there's ways to switch that. Ben Eater talks about all this stuff. So I'm going to put a link to one of 2 or 3 of his videos, probably 3 videos, which will in a matter of like, I don't know, an hour or so, will give you a great understanding of how to put a chip on a board with a clock, how to interface it to another chip. And in your mind, if you think about a SID chip, you can get an amazing amount of work done and write some simple code on a breadboard. If you don't even need a Commodore 64 or an F256 for this, on a breadboard you can put these 2 chips and a couple of the other chips on here, and then maybe add like an inexpensive audio amplifier over here on audio out, right? You've got it sunk there, a resistor. This is where your amplifier would go, and you could write some code and do some great things. Or you can just write code on your F256, and that's what we're here for. Is the end of it, I think? Yep, that's the end of it. These are some more ads that they had for this update. Yeah, that's nice. Nothing too interesting or exciting. I spent a lot of time on this sheet. Hopefully I've piqued your interest in some way. We're going to quickly change gears now, and I'm going to run over to some of the data we closed the last video with. So let me change the screen here. Okay. So we talked about this last time. This is the last thing we're going to talk about today, aside from the kind of the teaser of what I'm looking to do with this guru mode. 2 or 3 things changed from last time. One is that I put these vertical columns in. I've highlighted every other column for a reason. And then another thing is I've added more highlighting to groups of bytes, right, which I called phrases last time. I've also highlighted 16 of the phrases, which I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16. I think it's 16 here. Just because I wanted to show, like, of all of the data, this is the entire song, right, from here to here. I think I say it was 1,400 bytes. I forget the total. This is the shortest song, by the way, of the Commodore Christmas songs. Of all the data, you're looking at 16 to here. So this is about 16 phrases worth of data, and of course the variable length. We'll talk about that in just a moment. But if you were to eyeball, that'd be 32, 60. So figure there's 128 phrases in this song. And if you were to count beats, you might get to some place where you were talking about eighth notes, perhaps, depending upon the complexity of a song. And we'll talk about clock next time, probably. But I just want to give you an idea of how you can look at this massive data and make sense of it. The number one thing to start with is that, when the introduction was last time, but let's start over and say that the number one thing to start with is that all of the SID information, at least for the Commodore Christmas player, starts with a byte that's not used. And sometimes some of the songs have A, some of the song AA, some have 00 in there. The first byte is the second position, or byte 1 of it's 4158 in this case. And every one of these vertical columns is a control byte. Every one of these non-highlighted columns, vertical also, but I should say the non-highlighted columns are data bytes. So if you know anything about 6502 assembly, or if you know anything about the poke command in BASIC, you know you need to have an address. You know you need to have a value, right? So you're loading information from someplace from memory, and you're storing it into an address. Likewise, in an instruction, say I'm going to type on this real quick. Let's do it here. If I were to type LDA number $01, okay, I'm saying this is immediate mode use of the load accumulator command. I'm loading the number 1 into the accumulator. This this kind of representation of assembly code is what's known as opcode on the left side and operand on the right side. Now I'm going to put 2 other instructions here, and this will make a lot of sense to people who know 6502. If I said STA in D401, let's say, good, that is a multi-byte operand, right? This has a single byte operand. This has a multi-byte operand. Now I'm going to add one last instruction. A lot of people probably know what it's going to be. Well, maybe you're not going to know. Just this one, RTS, return from subroutine. This is a single byte opcode with no operand. So assembly language has any of these 3, right? You either have 1 byte, 2 bytes, or no bytes following the opcode. In this SID data, there's always an operand to the opcode. So the opcode, if I could call it that, this is, right? It's not only assembly language, but the opcode is, what am I going to do? What's the action? The action is I'm going to affect the frequency of oscillator 1. I'm going to affect the gate of oscillator 1. So what I have here is highlighted columns to say everything in the brownish color are the opcodes, and everything in the non-highlighted columns are operands, right? So this is controls, and this is data. That's probably the best way to say it. So let's walk through it just briefly, and I've highlighted here and underlined the frequencies, right? So these are frequency opcodes. There's 0 and 1, 7 and 8, E and F. Now I'm going to scroll down to a little graphic I made, which talks about 3 bytes I was going to talk about today. The frequency 0 and 1, and for voice 2 it's 7 and 8, and it's E and F for voice 3. And the 3rd byte we're going to talk about is the control byte, which is at 4, B, and 12. So I'm moving quickly here, but hopefully you're following along. And I'm doing this to remind you of what we talked about yesterday, which was, let me go try to get, there we go. Oh, hang on. See, I've got all these graphics on top. That'll work. I left off yesterday with this highlighted, and I said this is the first phrase. Ignore this over here, of course. This is the first phrase, and the bytes I'm addressing here are not necessarily consecutive, I said. But here in this first group, they are consecutive, and it's probably very common that the first thing you want to do is to initialize the SID registers. So that's what this first phrase does. It also happens to be dumping values into byte 0 and 1, which are the frequency. So if you look up 19B0, you'll find, is 19B0? It's probably low byte, high byte. If you look that up, you'd probably find that represents the first node of the sequence. And we'll have to see what that is. I'm not going to do it today. Byte 2 and byte 3 are pulse width if you're using a pulse waveform, and because it's set, I'm going to take a wild guess and say that this does use the pulse waveform. In fact, I know it does because I looked ahead of time. I'm challenged with this. Do this here. I'm going to make them bold. Bold. There we go. Okay. Byte 4 contains a 41. So what does a 41 mean? Let me scroll down to this chart here. I can go back to the Commodore spec sheet too. But this column here, which is byte 4, B, and 12 for voices 1, 2, or 3, is split in the 2 nibbles I mentioned when I was drawing on with the mouse virtually on the spec sheet. And I said that the upper nibble is the waveform, and the lower nibble is the gate and some other things, which we're not going to talk about. Let's look now back at the data. I'm actually going to drag this up here because I created this so that it would hopefully line up. Let's see if I did a reasonable job. This goes this way. 41. That's what I want. Okay. So byte 4 contains a 41. The 41 is broken down into 2 nibbles. The first nibble, or the higher nibble, is a 4. The low nibble is a 1. The high order bit of the 4 represents the pulse waveform. The low order bit of the 1 represents gate on. And I'm tying it down to here. That's bit 0, gate 1. We're not dealing with any of these things here, right? It's only a 1. It's not a 2, 3, 4, 5, 6, or 7. And we're not dealing with any of the other waveforms here. We're just dealing with the pulse waveform, which is bit 3, 0, well, bit 2. It's the third in this nibble, but if this is bit 0 of the nibble, bit 1 of the bit 2 of the nibble, the value would be 1, 2, or 4, and we're saying it's a 4. So that's kind of a quick decode of this first sequence of the first phrase, at least up to the 4th byte or the 5th byte, but it's the 4 byte. And then I'll say that this is D. I'll go say again, this is D400, D401, D402, D403, D404. There's more after this. We're not going to talk about that today. We're talking about 3 bytes only. But let's now move on to the second note that's played in sequence here. And again, not all phrases are going to be a note. Perhaps it could be something. Could be setting a register for next time, or it could be setting something dynamically that isn't going to necessarily sound the note, but may alter the sound. So the second phrase begins here in green, and this byte here belongs to the 40, which is the end of phrase. So now we're at the 0 byte, and now we're at the 0-1 byte, and this is frequency information, byte 0 and 1. And now if you notice something interesting happened, and that's that we've got the 0 byte, the 1 byte, the 6 byte. What happened to the 2 and the 3? Well, probably not using a pulse waveform here, but maybe it's doing something different completely. Maybe it's happy with what it is, and all it's doing is playing the second note, keeping all the other settings the same. So let's just follow through. There's 6, and then we'll move up to B. And B, we're up to this voice 2, right? So let's see what register 6 was, because it's interesting that they throw a 9F into 6. I don't have it on my sheet here. I'm doing this for the first time. Let's have a quick look. 6 is sustained release. It's a sustained release for voice 1. So they're altering the sustained release of the end. They're changing the envelope, it seems, from whatever the initial value might have been. So that's interesting. So let's move on to the third one. The rest of it is other oscillators and other changes. Let's move on to the third one just for fun and say, so now the third phrase, there's the 0 here belongs to the 40. That's skipped. The 0, I didn't underline these, but this is frequency again. So looking at 9A, we're looking at 1.5 is data, 0 and 1, and then it goes to 6. Again, it's changing the wave, the envelope, and it's the same data, isn't it? Here's 6 with a 9F. Here's 6 with a 9F. Interesting. Anyway, one of the great things you're going to find out tomorrow, this is a spoiler, is that I go into single step mode. The Foenix Christmas demo is I'm working on it now, but it has a single step mode. In fact, I was using when I was debugging the program. And you can use a joystick, and you can press one note at a time. So what we'll be seeing, instead of hearing me and trying to talk about bits, bytes, and nibbles, you'll see real time and yourself real time. I'll post the binary that you can push the button in on the joystick, or push the joystick up or down to make the player do something special. And the goal here is to visually represent what changes are being made inside the SID chip in characters. I'd love to be able to do waveforms and a bunch of other stuff. I just don't have time for it. So I've been rolling this for a long time. This video may be 20 minutes long actually, but those are most of what that's most of what I wanted to talk about today. Hopefully I didn't lose too many of you. There's a lot to learn here, and if you followed, or maybe go back to this another time, you'll probably pick out a couple bits that you didn't catch the first time, as some of this starts to make more sense. It's a fairly simple topic if you've worked with this stuff before. If you haven't, you can pick up these things easily. I mean, it's not rocket science, and hopefully the step-by-step approach today was a big ramp up from yesterday, but tomorrow it'll tie a lot of this together as I present not necessarily code, but I present how to use this guru mode of the F256 Christmas demo, at least in character mode. So let me quickly get to my agenda and see if I covered everything. I think I did. I talked about this. We talked about the SID data in context. We talked about Ben Eater and in theory how you would connect it up. We talked about diving into the spec sheet. We walked through the spec sheet in a detailed fashion, covering probably a third of it. We'll probably only cover another third of it with envelopes and other things in the coming days. And then I showed you a 7-minute video of me noodling around on my synthesizer, and that's it. At the end of day 2. Hope everybody's enjoying their holiday if they're still taking a holiday. And hopefully, if you're not taking a holiday, you're working but not working too hard. And we'll catch you next time.